continuation of the same topic. That is, we are going to find out the space occupied or the volume occupied in different cubic structure. We have just discussed earlier from the previous video. That is, we have just calculated the space occupied in a simple cubic unit cell. Now we are going to find out what will be the total space occupied, or what will be the volume occupied by what? By the constituent particle in case of what? In case of a face-centered cubic structure. Face-centered cubic structure. Face-centered cubic structure. Or you can say, in short, FCC. We are going to find out what will be the space occupied in FCC, right? I have to draw the structure of these FCC. This is the structure of FCC. Please keep that in mind. Each corner here represent a constituent particle. Each corner represent a constituent particle. 1, 2, 3, 4, 5, 6, 7, 8. Now I'm gonna join this to give me the geometry. Actually, if you remember, in face-center cubic, or in FCC, apart from the constituent particles that are present at the corner, there are also extra constituent particles that are present at the center of each face. Now the face this side, this is one constituent particles. Face below, another constituent particles. Face this side, one constituent particles. Face above, one constituent particles. Face that side, that back side, I'm gonna put one constituent particles, and face this side, I'm gonna put one constituent particle. So all together there are 6 face and 6 extra constituent particle at the center of each face. I'm gonna take, for my calculation, I'm gonna take this face diagonal. I'm gonna take this face, and this is the face diagonal. This is the one. You got this? Please keep that in mind, that this sphere is in touch to this sphere, is in touch to this sphere. But as of now, I'm showing only the center, so it does not show that they are in touching to one another. They are in touching to one another. But in realities, actually it should be like this here. Now this one is in touch to this one. It should be like this. Now this one is in touch to this one. Now if I take this face diagonal to be AC, this part more. If I take this face diagonal to be AC, then this AC will be equal to how many radius? Will be equal to 4 radius, as you've seen. 1 radius, 2, 3, 4, isn't it? Just take a look here. I'm gonna draw it clearly. This one, where I'll draw here. There will be 2 radius here, 2 radius here, 4, 2 radius here, 6. But I am taking only from the center of this one up to the center of this one. This part I'm taking, isn't it? So this part is 1 radius, another radius, another radius, another radius. All together, as you've seen here, there are 4 radius, isn't it? So likewise, this face diagonal which I'm taking here, AC is equal to 4 radius. And likewise, the H length of this FCC, you can take any one. H length of this FCC will be equal to A. You may take this part, this part, this part is equal to A. This is the H length from here up to here, or you can say from here up to here. This is the H length. You got this? Let's start with our calculation. As the sphere are touching, as the sphere are touching to one another, what do you see? In this case, This phase diagonal, which I represent AC, will be equal to how many radius? Will be equal to 4 radius. You can refer from this figure. I'm thinking this phase diagonal will be equal to 4 radius. Or if I take the H length A, any part of this A will be equal to 2 radius, right? Now, I will refer this right triangle, say sorry, I will refer this right triangle ABC, right? Okay, now from right triangle ABC, okay, if you apply Pythagoras theorem here, you will find out that AC, that is this phase diagonal, AC should be equal to how much? Should be equal to the sum of the square of the two opposite sides. That will be AB square plus BC square, isn't it? AB square plus BC square. Okay. AB is also the H length. BC will be also the, sorry, AB is the H length and BC is also the H length. So the value of AB will be equal to A square. Value of BC will also be equal to A square. If you sum them, AC is equal to how much? It's equal to 2, how much? 2A square, isn't it? Right? 2A square. Now this square and this square root will cancel. The value of AC, sorry, the value of AC will be equal to, AC is equal to root 2A. I think this is the actual value of this AC. You got this? Alright. We have also find out that the volume of the unit cell, volume of the unit cell. What is the name of this unit cell? Is phase center cubic. Volume of the unit cell is equal to how much? Is equal to A cube. What is the value of H length here? The value of H length will be equal to, oh, hang on a second. Before I come into this volume, let's find out what is the value of A here. What is the value of A? Now this phase diagonal, sorry, I cancel this part first. Now this phase diagonal AC, I've just shown you, AC is equal to how much? AC is equal to 4R, isn't it? I'm gonna put this value now. This can forget this volume first. I'm gonna put this value now. AC is equal to how much? AC is equal to 4R. Now root 2A from this part is equal to AC. What will be the value of AC? The value of AC will be equal to 4R. And from here, if you want to find out the H length, A will be equal to how much? A will be equal to 4R by root 2. Yes, this is the value of A, isn't it? Value of the H length. A is equal to 4R by root 2. Therefore, volume of the unit cell, volume of the unit cell is equal to how much? By formula is equal to A cube, and the value of A will be equal to 4 by 3, 4R by root 2, isn't it? I'm gonna put here 4R by root 2. So 4 by root 2R cube. This will be equal to 32 root 2 R cube. This is the volume of the unit cell. 32 by root 2, 32 by root 2 R cube. What is the total number of spheres that are present in a phase center cubic? If you remember, number of sphere or constituent particle in FCC is equal to how much? There are, sorry, number of sphere in FCC. Each corner atom is shared by 8 unit cell. There are 8 corner atom plus Each corner atom is shared by two unit cell. There are six phase. Sorry, each atom that are present at the phase is shared by two unit cell. There are six phase. So altogether, from here you'll get one. From here you'll get how much? 3. So 1 plus 3 will be equal to 4. Altogether, there are 4 spheres in an FCC, isn't it? Therefore, volume of 4 sphere, volume of 4 sphere is will be equal to, we all know the formula of the sphere is 4 by 3 pi r cube. There are 4 sphere in FCC, so I multiply by 4. Altogether, you have here will be 16 by 3 pi r cube. You apply the formula for packing fraction, you will get now. Therefore, packing fraction or packing efficiency, packing fraction is equal to, packing fraction is equal to volume of the sphere divided by volume of the cube. Volume of the sphere divided by volume of the cube. What is the volume of the sphere in this calculation we have just made? Volume of the sphere is equal to 16 pi r cube by 3 divided by volume of the cube, which is 32 r cube by root 2. After all, when you cancel, you will find out that pi root 2 divided by 6, putting the value of pi is equal to 3.14, multiply into root 2 divided by 6, you will get 0.74, or you can say or percentage occupied is equal to 74%. Now what do you see in case of FCC, or you can say FCC is more efficient way of packing, or is more efficient modes of solid, because in an FCC the space occupied by the constituent particle is 74%, whereas in case of simple cubic we have just seen the space occupied is 52%. Therefore, FCC is a more efficient way of packing rather than a simple cubic.